maybe next section is that, I don't know, is that the last section? I don't think that's the last section. Anyways, Stokes Theorem. So there's conditions of your vector field being nice and differentiable and stuff around the domain. But in general, we have a vector field F going from R3 to R3. And we have our surface and then the boundary of the surface being defined. So S is the surface, and then it has to be an open surface. So I'll put open in parentheses, but more importantly, instead of using C for the curve that represents a boundary, let's use S with a little partial, and remember the partial stands for the boundary. Of S. And there's an orientation that's important here. So the surface has orientation. And so the boundary, therefore, also has orientation. And we talked about the right-hand rule orientation for this, and we'll continue to talk a little bit more about this idea as we do more examples. And so the actual theorem, the statement of the theorem, says that we have a double integral. Well, call it a double integral, but it's kind of like a surface integral. But then it's an integral over a vector field, so it becomes a flux integral. So the book uses surface integral and flux interchangeably. I'd like to try to separate those and call this more of a flux integral. So it's over that surface, and the vector field that's going to go in here isn't the exact same vector field that we're talking about, but rather the cross of the vector field, which is still a vector field. And then the book and a lot of places use .n ds, but I'll shorthand it to say ds, but put an arrow on top of the s to say that we are talking about a flux integral. And this is supposed to equal to a single integral. That single integral is not a regular single integral, though. That's actually a line integral. So it's a line integral, and a line integral, we want it over a curve. And the curve that we're talking about is C, or ds as we called it, the partial or the boundary. And this curve, if you think about this, this is a boundary of a surface. So a boundary of a surface necessarily has to be a closed curve. So the surface is open, but the curve that results as a boundary of an open surface has to be closed. Think about that. If you think of any examples of any open surfaces with a boundary, a lid, a curve, that curve has to be a closed curve. And so for line integrals to denote closed curves, we use a little circle. In fact, we use a circle with an orientation that goes in a counterclockwise direction to say that we're looking at a positive orientation here. And that orientation is positive. It just needs to be able to agree. When we say positive orientation for the curve, it's just the curve that agrees with the orientation that comes from a surface. And that will be the original function dotted with our d little s, or little s standing for the parameterization of that closed surface. Now, some problems that you get will give you a line integral and say, hey, can you do this line integral for me? And you look at the line integral and say, oh, that looks too hard. Why don't I do the double integral or do the flux integral instead? In some cases, it might be easier. But in most cases, you're actually going to be given a flux of a curl, and then you're going to say, oh, that looks too complicated. I'm just going to go ahead and do the line integral instead. So the idea behind this theorem is that there's problems where you can go from a flux to a line integral, and problems where you go from a line integral to a flux integral, and it kind of depends on how the problem is given and which one will end up being easier for you. And then there's another trick to this where you're doing a surface and a flux integral, and but the surface is too complicated, and so you pretend to bring it to a line integral and then decide that there's another surface that you can integrate over that might be a little bit easier. So you're given a flux of a curl, and then you're going to still do a flux of a curl but over a different surface that's going to be a lot easier. All right, so let's label these. We said this is the flux integral of a curl of a vector field. Let's just say of F. So this is a flux integral, and here this is a line integral of F over the boundary of S. So we're still talking about the same surface, although that surface may morph into something else with the same boundary. I don't know. So this is where we left off last time. We introduced this. We talked about a couple of ways to solve for these types of problems. And so the next thing to do, I guess, is just to dive in and try to take a look at some problems that might use Stokes Theorem. All right, so let's do that. I have your homework set. You only have 5 problems here. I don't know. Seems like very few, especially if I'm going to do one. Or 2. Let's do.
This one's hard. No, I like it.
That looks too hard. I don't want to do it if it's hard.
Let's just do the last part.
What's the last part?
I know, I keep getting it wrong.
All right. All right, let's try. Let's see what we can do with this problem. So it says to use Stokes Theorem to find the line integral. So here we're starting from the right-hand side of the Stokes Theorem, the line integral. And here you're given this vector field where C is a curve of intersection between the hyperbolic paraboloid. This is your hyperbolic paraboloid. Remember that Pringle potato chip saddle? And then your cylinder, x squared plus y squared is equal to 1. And so oriented in a counterclockwise direction when viewed from above. All right, so let's think about the orientation and then maybe not spend too much time on it. But let's think about the orientation. How we're going to think about the orientation is we actually need to draw this. But I don't know, do you guys know how to draw a saddle?
Yeah.
So a saddle, some wavy thing, I don't know. But it's like a Pringle, right? But the intersection is with this cylinder. See if I could draw this and then take it away again. So this is your cylinder, right? And you're really just concerned about looking at it from the top. You're concerned about this saddle having this orientation that's going in a counterclockwise direction when viewed from above. So the orientation has to be going this way, right? So if the orientation is going that way for the curve, which way is it going from the surface? First of all, what surface are we looking at? Are we looking at the hyperbolic paraboloid, or are we looking at the cylinder for the surface? The other one. So the cylinder just turned out to be our boundary that helps us make our boundary, but the actual surface itself is the hyperbolic paraboloid. So this is the actual surface that we're looking at. In fact, if you want to take the cylinder out, you can. You guys taking notes in pencil? Or you can put it back. Can you do that with your notes? All right. So, any case, if you follow your right-hand rule for this orientation, which way should the normal vectors for the flux integral, so it has to be a flux now, we're going to exchange this problem of a line integral to a flux. So let's make a note to ourselves, note to self, given line integral that we need to compute. I'm going to change that into flux. Using Stokes. Okay, so because we're using Stokes theorem, we're going from one integral to another integral. The orientation is important. We know the line integral orientation already. Now, which way is the flux integral orientation going to be? So the flux integral is on the surface, and I see the surface. We've agreed that the surface is going to be the hyperbolic paraboloid, not the cylinder, but the hyperbolic paraboloid. So I can see the hyperbolic paraboloid as a Pringle chip. Now, is a normal vector going to be going up or down? That's the question. Should be going up. If you follow this Pringle chip, the sides of the Pringle chip with your right hand, whichever way your thumb is pointing, your right thumb is pointing, that's going to be your normal vector. So in this case, the normal vector is going to be pointing up. Okay? Go buy some Pringles. Check it out. All right. So now that we have the orientation figured out, let's actually jump to the actual integral. And this says that a line integral starts by looking like this, the boundary of S. I'm going to change C to the boundary of S since we're going to define this S surface. And we're going to change this into the surface itself, which is the hyperbolic paraboloid bounded by the cylinder, and then the curl. So we need to find the curl of that vector field. Taking the curl of that vector field maybe, hopefully, would make it simpler for us to deal with. So we need a couple of things to work with. We need the curl of the vector field. So we have the vector field F here. And then we need to take the curl of that. So let me rewrite F over again. I don't know why. It's x squared y, comma 1/3 x cubed, comma x times y. And so from there, I want the curl of the vector field, which is going to be yet another vector field, right? So the curl of the vector field in the I direction, think about, imagine this, or actually maybe you'll have to write it out. You've had homework in this, so I'm hoping you have practice in taking curls already. So the curl is going to be with respect to, it's the z component of the vector field with respect to y. So that's x, y with respect to y is x. And then the y component of the vector field with respect to z, and there's no z's there, so that's just going to be 0. The middle term, there's going to be some minus sign or something like that. The derivative of the z with respect to x, and then the derivative of the x term with respect to z, which again is 0. And then the last is, it's like the Green's theorem that thing inside of Green's theorem. So it's going to be the derivative of q with respect to x. That would be x squared. And then the derivative of p with respect to y, which is x squared again. So again, that's going to be 0. So that's nice. Your vector field really simplified. The curl of the vector field now is x comma negative y comma 0, which looks like it's going to be a lot easier to deal with. Okay? All right, so now that that's done, the other part of this is to parameterize your surface, and your surface is this, this thing. So there's, again, several ways to parameterize this. Let's parameterize it using the regular graph parameterization. So I'll do this in red. I call it graph parameterization to say that x is x, y is y, and then the z is whatever the function is that they gave us. So they gave us a function. So the graph parameterization, I'll label that as r. R is a function of x and y, or u and v is what we sometimes say, but I'm saying x and y. Because it's a graph parameterization, and a graph parameterization is always going to look like x comma y comma whatever that z is. So the z is y squared minus x squared. Now remember, in like graphing programs like the 3D plotter, if you were to graph this with using the 3D plotter, you would label it with u and then v squared minus u squared, but we're just writing it out by hand, so we'll use x's and y's. All right, so we got the graph parameterization for this, and we want to find the normal vector, and the normal vector is, do we have that remembered already? It's like the, so Rx cross product with Ry. Now instead of doing the Rx, Ry, Rx, by the way, is like 1, 0, and then whatever, right? And Ry is 0, 1, whatever. And those whatevers are just the components of the gradient. Negative, right? And so when you cross them, you get negative the gradient. So the gradient comes from this function, if we were to compute the gradient. So pretend that this is z. X is going to be negative 2x. Zy is going to be positive 2y. It looks like it's that. So it looks like it's going to be negative 2x, comma, negative 2y, comma, remember what that last one was? It used to be negative 1, but then we crossed it differently now, so it's positive 1. Yeah, so not this capital F, but this function f. So if we pretend that this is our function f of x, y, and we're working strictly with the surface here, then this is fx negative fy and positive 1. If we need to reverse it, yeah. But we want to keep it like this to try to figure out what our orientation is. I put an extra negative somewhere. Which one has a negative? Which one? One of these is negative. One of these should be positive. So this should be positive. Because this is negative x, but then I put negative fx is what I want. So negative is positive. And this becomes negative 2y and then positive 1. All right, so the orientation for the surface is defined by the direction of the normal pointing upward is what we decided, right? And so as long as this is positive 1, it doesn't matter what x or y value you're at. It doesn't matter where you are on this. It looks like your z component is always going to be going up. So this is an upward orientation for our normal. So this I would call OPP, orientation preserving parameterization. So I can stick with this parameterization because it's positive, and we want the normal vector to be up, going up, so we want it to be going positive. Well, because of the right-hand rule. So we drew these vectors because of the right-hand rule, and so we decided that our orientation for the surface would be upward orientation, because they want the curve to be a round orientation, counterclockwise orientation from the top. So because it's a counterclockwise orientation from the top, we use our right hands to try to figure out which way our drawing, our normal vector is going to be. So if it was going clockwise, then our orientation would be downward, and then this parameterization that we came up with looks like it would be the opposite. So it would have been orientation reversing parameterization, ORP, which means when we get our answer, we'll just throw a -1. You can keep the parameterization even if it's the opposite, because it's going to be the same work, except you'll have an opposite answer, negative. Yeah. So when you get your normal vector, your ds vector, that's essentially your normal vector. That's when we can figure out whether our orientation was in the correct direction. Okay. So we'll keep this orientation. It looks good. And now we just put in our x value is equal to x, our y value is equal to y, and our z value, well, there's no z's in here. There's no z variables in here, so we don't have to worry about it. Had there been z's in this curl, then we would have had to put in the y squared minus x squared in for z. But as it stands, there is no z, so that's good. So all we have is x and y, and we have 2x, 2y. So let's get to the surface integral here, our flux. So to get to our flux, our flux integral over S of that curl So the nice thing about this graph parameterization is the x stayed in x, the y stayed a y. And so we don't have to change the x's and y's here because x is x, y is y. Except, like I said, if there had been a z somewhere over here, then we would have had to deal with z's. But in this case, there is none. So now this is going to become a double integral. Oh, I forgot one thing, sorry. Because we're going to change this into a regular double integral, I need to know the domain. So let's look back at the picture. When I wrote the parameterization, what's our d equal to? Because that's going to help me figure out my limits for my double integral. Any ideas what the d is equal to? Well, technically not the cylinder, because the cylinder is just the outside, but the shadow of the surface on the xy plane, because it's on xy, because it's a graph parameterization, we're looking at the shadow on the xy plane, which is a circle. And instead of writing it the way they wrote the cylinder, I'm going to say less than or equal to 1, because it's not just the circle on the outside, but the whole disk, including the inside. So our domain is x squared plus y squared is less than or equal to 1, which is now going to make me change this into polar after we set up the double integral. So that's our domain, and the reason I wanted d in there because I'm getting my double integral set up here, and so I'm going to use my d. Okay, so inside of the integral is a dot product between my vector field, which is the curl, dotted with the ds, which is the parameterization, which we found to be OPP. So I have an x, maybe I'll put this up here. It's x comma minus y comma 0 dotted with the normal 2x negative 2y positive 1. And so those two combined, dotted together, I'm going to get 2x squared minus minus becomes a positive 2y squared. Oh, that's nice, because I was just thinking about polar coordinates for this. Now I can change this to r squared. And then the ds is actually this thing with the dA, dx, dy. And I can call it dx, dy, or dy, dx, or just d capital A to represent either. Okay, so remember, this is from the vector field, and this is from the ds, and this would also include dx, dy, or dy, dx. All right, so now let's go polar. And we've done this a bunch of times already. Circle of radius 1, a disk of radius 1. Your r goes from 0 to 1. I have 2r squared, x squared plus y squared, an extra r, dr going from 0 to 1, and d theta going all the way around 0 to 2 pi. So I have the integral from 0 to 2 pi with respect to theta, so that's just 2 pi. And then I have 2r cubed with respect to r, so I think that's going to be r to the 4th over 4 times 2, so r to the 4th over 1 over 2. And then you put 0 in and 1 in for r, you're going to get 1/2. So this answer here looks like it's just going to be pi. Okay? All right, so that's how we get to use, that's one way to use Stokes Theorem, is that we're doing a line integral. Instead of doing the line integral directly, which we could have done, we're going to go into a flux integral.
For this one? Sorry.
Yeah.
The last part of it asks for parameterization of the curve.
So that's just for fun.
In terms of t.
Yeah. So we'll do that. That's like a little extra. Should I start a new page or just continue down here? So we don't have to do it for this problem because we're essentially done with this problem in terms of getting the actual integral. But if we were to do the line integral directly, then we would have had to parameterize the curve. So what do we know about the curve? If we look at the curve from the top, it looks like it's just a circle. Circle of radius 1. And if we look at the curve from the side, it looks like it's waving. It's going along the thing. So it's waving according to the surface. So it looks like the z's go up and down with respect to the surface. But looking at it from the top view on the xy plane, it's just a circle of radius 1. So I can, if this was just a two-dimensional parameterization in 2D, your parameterization is just sine and cosine, right? Cosine t, sine t. So what happens there is that if that is going to be the xy, it's like looking at a map and tracing out your path in the map. All you're looking at on the map is your x and y. Now, it's not until you actually go on a road and you feel your altitude going up and down is when you include your z. So in terms of thinking about it that way, your actual mapping when you're actually on the road is going to be the same as the x and y mapping on the map on a flat two-dimensional plane. So your r of t is going to be cosine t sine t. Now your z component is just going to depend on the terrain, on the surface that you're on. And depending on what x and y value you're in, you're just going to plug in your x and y value into your surface. So your surface is this. So, oh, by the way, the radius is 1, so there's no coefficients here, right? So your surface is y squared minus x squared, so that looks like it's just sine squared t minus cosine squared t. And then that should be good to go. I suppose you can simplify this using some double angle formula, but let's check our answers, I guess. So this one, you just have to make sure that your cylinder is a radius 1, and then you're looking at the correct view. And for this one, find the parametric equations. Enter your answer as a comma-separated list of equations. Let x be in terms of, let x and y be in terms of t, where t goes from 0 to 2 pi. So here they tell us our t goes from 0 to 2 pi, so we can just go with that. Do you need to put x equals? X equals cosine t, maybe, comma, sine t, comma, z equals sine, yeah. Guess you need to be careful about squaring this, right? Sine t quantity squared. Don't mistake it from, sine parentheses t squared. Cosine t squared. All right, so that worked out. Our answer was pi. I hope that was correct. And then we just didn't answer this one because you guys can figure it out. All right.
Thank you.
So the other one's another line integral. Let's see if we could do problem number 1 is the only one that let's try to do the first one. I don't know if I want to do this one. Oh well. Let's do it. So here they want the curl of f over ds over the surface that consists of the top and 4 sides, but not the bottom of the cube, with vertices of plus and minus 3 with an outward orientation. What? So let's get a handle on this surface that we're looking at, as we're looking at this surface over here for the curl, for the flux integral. And let's see, surface. So this is a simply connected surface The good news is that it's an open surface, so which would make it so that we can use Stokes Theorem. So if we were to do this directly using flux integrals, 1, 2, 3, 4, 5, we would have to do 5 flux integrals, right? We'd have to do one for each surface, so maybe surface 1, surface 2, surface 3, surface 4, and surface 5. So there's 5 surfaces to deal with, and technically we would have to parameterize each one of those surfaces and then, you know, find limits and stuff like that. So that seems like it's going to be too much. If we use Stokes Theorem, then we're going to trade in our flux integral to a line integral. So we're going to go from a flux which is this thing, curl F is the symbol that I'm using for curl F. You can interchange that. I hope you knew that already. To a line integral. So our line integral is going to be over the boundary of F. So the bad news is that there's going to be 4 pieces to our boundary. It's not a nice circle where I can just do one parameterization. I have to do 4 parameterizations. So let's deal with that. Let's call this C1, C2, C3, and C4. So I'm going to have to parameterize 4 times. Now hopefully it's not too bad. Let's see how it's going to work out. Do you see our dilemma? Do you see where we're going with this? Let's parameterize C1. Let's say C1 was, so these are vertices. So let's say our C1 goes from positive 3 in the X, negative 3 in the Y, negative 3 in the Z. That's the point. And it goes to this other point where it's positive 3 in the X, positive 3 in the Y, and negative 3 in the Z. So our C1 is a line segment from 3, negative 3, negative 3 to 3, 3, negative 3. Okay? So do you guys remember how to parameterize a line segment from one point to another point? You have to find the direction vector. So the direction vector would be head minus tail. And the direction is important here. Oh, wait. Let's figure out the orientation. The surface itself has an outward orientation. Now this thing's getting really confusing. Imagine you have a box. I have a box with an outward orientation, and there's a hole in the bottom of the box. So the bottom of the box will end up being our boundary, right? Now, if you follow that right-hand rule and to say that with an outward orientation, your fingers, your right fingers are going to be curling and your thumb is going to be pointing out of the box. Let's take one side of the box and focus on one side of the box. And say this is the front side of the box. Outside orientation is a vector pointing right at you. Okay? And so you're on this box, your thumb is going, okay, my fingers are going to get wrapped around this way. Right? So what happens is that as you get closer and closer to the boundary, your fingers, your thumb's pointing outward, your right fingers are going to move the boundary, which is just the bottom over here, in a particular direction. Does that make sense? And it looks like it's going to move the boundary, if this is the boundary, is going to move the boundary in this direction. So it's going to move this boundary in this direction. And if you follow the rest of them, you'll see from the top view, it looks like it's going to be going in the counterclockwise direction, which means this point going from 3, minus 3, minus 3 to the point 3, 3, minus 3 is the correct direction. So head minus tail, I get a 0 for x. My y is going to be minus the head, 3 minus negative 3, so it looks like it's going to be 6. And then minus 3 minus negative 3 is 0. So the direction looks like it's this. So to parameterize this, this is a curve, so it only has one variable t. And then it's going to be the original point, which is 3 minus 3 minus 3. That's a starting point, plus t times the direction vector, 0, 6, 0. So if we simplify this and make a nice one big vector out of this, this is 3, this is negative 3 plus 6t, and then this is negative 3 plus 0. So that's our parameterization going in the correct direction, correct orientation, so we should be good to go. Okay, so that's one. We need to do 3 more, and we need to integrate. Should we integrate this first one, and then we'll think about doing the other ones? Or I should say, should we integrate this first one, and then I'll show you the easy way of doing this? Let's go through the integrate so that you can appreciate the easy way a little bit more. So if you were to go through this, this would be, let's call this curve 1, I think we called it C1. So let's do a line integral over C1 of the vector field x, y, z in the I direction, x, y in the y direction, and x squared y, z in the k direction. I'm kind of mixing notations here. I'm doing the parameterization already. So this parameterization for a line, by the way, is a parameterization where t goes from 0 to 1. So integral from 0 to 1. Now my derivative here, r prime of t, should have done this earlier, but it's going to be 0, 6, 0. It's really just a direction, right? That makes sense because the initial point is a constant, so that gets wiped out, and t times a direction vector. So it's really just a direction vector, which means, so for this, I need to replace everything with x is equal to 3, y is equal to negative 3 plus 6t, and z is equal to negative 3. But then I'm going to dot it with 0, 6, 0. So it looks like the first component and the last component of the vector field is going to be 0 anyways, right? So I'm just going to put star here, and then I'm going to put x is equal to 3, y is equal to negative 3 plus 6t, and then this will also be negative 3, or 3 squared, and then negative 3 plus 6t, 6t, and then negative 3. But again, since I'm going to dot it with 0, I'm not going to care what that is, so I'm going to put another star for that. So this is just going to be this middle term multiplied with this middle term because everything else is 0. So I get 0 to 1 of 3 times 6 is 18, negative 3 plus 6t dt. This looks like an easy enough integral. And if you go through the rest of the curves, C2, C3, and C4, you'll get, tediously end up with the same sort of integrals that are, they look like they're just as easy to work with. Okay? Only thing about this is that it's tedious, right? We have to go through 4 things. Then do the same for C2, C3, C4, then add. Okay, now, I don't want to do it that way. Let's take a look at this scenario again. What do I want? I want all this. So let's do this over again and look at the problem, look at the picture, and see if there's another way to do this. Okay, so we said that we have these surfaces. Our surface S has 5 surfaces. S1, S2, S3, S4, S5. I'm using the little u for union. I was going to say just plus, but technically it's a set. So that's what that means, union. And there's 5 of them, and this is open in the bottom, and so we decided that this is going to be our boundary with a specific orientation. So initially, my thought was to go from a flux integral that we're looking at to a line integral. Now, the line integral still has 4 curves, lines, 4 lines. Four curves to deal with, and this has 5 surfaces. So our flux integral had 5 surfaces. Our curve has 4. Our curve has 4 curves. Now, remember what I said about going from a flux to a line and then back to a flux again? So we've established now that this is a boundary for our surface. Right? So let's rethink this problem over again. We have now a new problem where this is our curve C, and we want to know what this line integral is. Right? So, does anybody know where I'm going with this? What's the same surface?
Something simple.
What's the simple surface?
A square.
What if we look at this square right here as a surface? That's a surface, right? That's just the bottom of the box. That's a surface. What if we just look at that square as a surface with a boundary of S? So let's call this surface S prime, which is clearly not the same surface as those union of all those 5 surfaces, right? If this is S prime, is a surface. Now if we take a look at this surface, then the boundary of that surface is the same as that curve, so we can rewrite a flux integral now with a new surface, not the same original surface, but the new surface that's way, way easier, and take the flux of the curl of that. By using a simpler surface, one surface. Now what's the orientation for my new surface here? Is my new surface will have an orientation, by normal it's either going up or down. So is it going up or down? Right hand rule, right? We got the orientation for the curve itself. So if you use your right hand rule and follow that around, our orientation will be going up. Okay, so we'll parameterize this and we'll see if it'll work out. All right, let's parameterize S prime. It looks like it's a simple graph parameterization, so let's just use x and y as our graph parameterization. And it looks like x is going to be x, y is going to be y. What's z equal to? No. No. Negative 3.
Why?
Z.
Yes.
Oh, why? Why? Okay. We're looking at the height, the z value of this square. Now this square is flat square. It's not tilted, which is good news. It's a flat square, right? So it's essentially a plane. Z is equal to negative 3, right? And then if we just trim that plane down to focus on this, then that's essentially what our surface is. Our surface is really an x and a y and a z value of negative 3. And we also have a boundary, our domain. I'll put colon here because I'll write it as x and y. X and y. Looking at it from the top, it's a rectangular, right? So in rectangular coordinates, Cartesian coordinates, we should have constant limits all the way around. And our limits just go from negative 3 to 3 for both of them. Okay, so now we have our surface, our domain. Now we just need the normal vector. And if this is our z value, right, this is our f of x, y value, which is negative 3. The derivative of negative 3 with respect to x, 0, so that's negative 0. With respect to y, 0. And then now the last one is 1, right, if we cross it in this particular direction. which does give us, in fact, that upward orientation. So this is OPP, sorry. This preserves our orientation because our normal vector is going up. Okay? All right, let's get our integral set up. Our integral over this S prime is going to be, I don't know why I'm writing this over again. Oh, I need to find the curl. Damn it, not done yet. We need to find the curl of this because we went back to the curl, right? So we need the curl of f. With respect to y, that's x squared z minus, with respect to z, is 0. With respect to, this is a negative. The last one with respect to x is 2xyz minus the first one with respect to z, which is yz. And then the last one is with respect to x, that's y. And then with respect to y, it's xz. That doesn't look much simpler. Well, hopefully it will become a little bit simpler after we put in all our stuff. So, keep this looking like a surface integral. We have for x, I'll put x. For y, I'll put y. For z, I'll put -3. So my curl is going to be, z is -3, so it's -3x squared. This is going to be I'm looking ahead now. I'm going to, my ds is 0, 0, 1. You see that? So actually, I'm going to just put star, star, and then I'm really going to be only concerned about this last part. Because after I do the dot product, which is what it's asking us to do, after I do the dot product with a normal, I'm just going to be concerned about that last component. So the last component, y is y, x is x, and z is -3. So the last component is the only thing that's going to be important for us because we're going to dot it with s, with our ds, which is 0, 0, 1. I guess I should call this dA. I guess I should call this a double integral. All right. So after we do the dot product, we have our limits. Our limits go from -3 to 3 for both, so I'm just going to write it down. I have a y plus 3x, and then our dA is dx dy, or dy dx, because they're the same limits anyways. So this should be an easy enough integral to do. So now we're dealing with one integral instead of two integrals, and this one integral is a double integral, or instead of 4 integrals, I think was what we were going for on the last page. So now we just have one integral. It's a double integral, but the integrand is easy. So I was getting carried away doing all these computations, but as you've noticed, one of the key things to look at here is that maybe you start writing your work, but then try to look ahead. This is a flux integral, which is going to be a dot product of your curl of the vector field with the normal vector. So if you look at your normal vector and you see something interesting, zeros are really, really interesting in these problems. If you see something interesting in your normal vectors, then you know that you're not going to care about the x and the y component here. I started to care, and then I looked ahead and said, hey, that's 0, 0, 1. I don't need this. I don't need this because they're going to be multiplied by 0. Right? And then once you do that, hopefully your integrand will be a little bit easier. Okay, any questions? Now I want to do one more thing with Stokes Theorem, and that is to go 2 dimensions. Guess what's going to happen in 2 dimensions? Stuff. All right, let's take a look at it. So if it's in 2 dimensions, then our vector field is only in 2 dimensions. So let's say P, Q, and 0. Then your surface is only going to have to be an area in 2 dimensions also. Call it R. So what do we need for Stokes theorem? We need the curl, right? So the curl is going to be, let's see, with respect to, oh, by the way, in 2 dimensions, I'm sorry, are you guys taking notes in pencil? You don't need to do this, but I just wanted to make it a little bit more explicit. That in 2 dimensions that we only have x and y and we don't have any z's. So P is a function of only x and y. Q is a function of only x and y. And there are no z's. There's no z component. There's no z variable. So because we're only living in 2 dimensions. So back to the curl. The curl, I want to take the curl of this. I cross out the first column, and I take the derivative of 0 with respect to y, and I take the derivative of q with respect to z. So the derivative of q with respect to z, because q is only a function of x and y, there are no z's in there, right? So that's just going to be 0. So likewise, the same thing is going to happen in the j direction. So in the j direction, I'll have the derivative of 0 with respect to x, the derivative of p with respect to z, and again, there are no z's in there, so the derivative of p with respect to z is actually 0. So the derivative, the last one is going to be the derivative of q with respect to x, and the derivative of p with respect to y. There you go. All right? So what does this say? Oh, also, if the surface is in 2 dimensions, flat in 2D, this is your R, then the normal vectors would be going straight at you, right? So the normal vectors is going to be straight at you in the z direction, 0, 0, 1, or just k. And then the positive orientation, which means this is going in the counterclockwise direction. So this is really forming up to be exactly Green's theorem. That's what we're going to get. So the line integral is the boundary of the curve, boundary of the surface, sorry, the boundary of that region R of f ds. This is our line integral into, well, technically it's a flux integral, so let me do the flux integral first. Pretend it's a flux. It's going to be 0, 0, partial of q with respect to x minus partial of p with respect to y, dotted with the normal vector, that's just the k vector, dA. Right? But the k is 0, 0, 1. This is 0, 0, this thing. So this really just becomes a double integral over the region of the partial of q with respect to x minus the partial of p with respect to y dA. So this is Green's theorem. So Stokes' theorem is just the higher dimension version of Green's theorem, or you can think about Green's theorem as a special case of Stokes' theorem because it's one dimension less. But if you look at Green's theorem and look at that thing inside of Green's theorem and convince yourself that that's really just a cross product in 2 dimensions, that's really just the k component, the z component of your cross product, then it's really exactly the same as Stokes. Okay? Even the orientation is going the correct way. That follows the same Stokes theorem orientation. All right? All right, so this is our second to the last big theorem. Our last one is going to be Gauss, and that's going to be another combination of 2 types of integrals. We're going to combine the flux integral with a triple integral. Fun. All right, see you guys tomorrow.